So this video is going to be on properties of quadrilaterals. People have asked me for quite a long time to make this video, and I've put it off for a long time just because there is a lot of information in here. It's going to be a bit of an information dump. So apologies for that. There is just a lot to get through. We will do some TMUA questions at the end of this video, so hopefully we'll just crack on with those when we get there. Let's start off though with squares. Squares are quadrilaterals that have 4 equal sides and 4 equal angles. Of course, you don't need to say 90-degree angles because 360 divided by 4 is 90, so you're kind of getting that done. Some more properties that it has though is that the diagonals, and TMUA talks about diagonals a lot, the diagonals are equal in length. And that seems kind of trivial, like surely all of them do that, but they really don't. So squares have equal diagonals in length. They're also, the diagonals bisect each other, which means this length here is the same as this length here, and likewise on the other one, this one is the same as this one. And also the diagonals are perpendicular, they meet at 90 degrees. And all of these conditions that I'm going to write down here for each of the shapes are going to be necessarily true for that shape. So for example, some parallelograms will also have equal diagonals, but not all of them, so that won't be a condition that I'll write in for parallelograms, but it is the case that all squares have equal diagonals and these things as well. They're also got symmetry through both diagonals. And they also have symmetry through each of the sides to leave 4 lines of symmetry in total. And that's basically it for squares. We'll leave those there and we'll go straight on to the next one, which is rhombi. I'm going to collect all this information together at the end after we've gone through each different shape. So hopefully you can look forward to that, and that'll be helpful as well. Okay, so rhombuses then. We've got 4 equal sides, and that's basically it. We don't need to be any more specific because, of course, if you make all the angles 90, that makes a square. But as we'll see, squares are just a specific case of rhombi. Like, they're not a different shape, they're just a specific case when you have 4 90-degree angles or 4 equal angles. So all you need to say for rhombuses are they have 4 equal sides and are quadrilaterals. That's all you need to say. And when you look at the diagonals, they bisect each other. They're not equal in length. They're not equal in length, but they do bisect each other. So whilst one is longer than the other one, usually, unless they're squares, they do bisect each other. So this length is the same as this one, and this one is the same as this one. You also have these diagonals being perpendicular, just like in squares. But there is no symmetry. There is. The symmetry goes through the diagonals only. So this shape doesn't have symmetry through the sides anymore, just through the diagonals. So just 2 lines of symmetry do. And as I just said, equal opposite angles, not so concerned about, but squares are just special cases of rhombi, right? Because they have 4 equal sides and 4 equal angles. After that, we get to rectangles, which are another special case. Are another shape in which squares live in as a special case. Rectangles, you just need to say have 4 equal angles. That is it. Therefore, those angles are 90 degrees, as we said with squares. But that's all you need to say. Right. That then means that there are 2 pairs of equal sides, but we don't really need to say that. 4 equal angles does it. Of course, the diagonals are equal in length, as before. They do not meet at 90 degrees, but they do bisect each other. So they're not perpendicular, but they do bisect. So this length here is the same as this one, and this one is the same as this one. Squares are just a special case of these. There is also no symmetry through the diagonals, just through the sides, as squares did as well. So those 3 shapes are very and we'll see a Venn diagram a bit later. But squares, rectangles, and rhombi are all very interconnected. Squares are the special case of both, just a special case in a different way. Special case for rhombuses because they also have the angles. Special case for rectangles because they also have the sides. The squares are very much a mesh of the 2 things. Parallelogram is the next one we'll do. Most people think of this when they think of a parallelogram. Most people define these as having 2 pairs of parallel sides, which actually then implies that each opposite side is equal. There's actually a really nice definition you can go with that actually encompasses all parallelograms, which is less intuitive but does work, which is just bisecting diagonals. If you have diagonals that bisect each other, in other words, this length the same as this one and this length the same as this one, then your shape is a parallelogram. That's an if and only if statement, which is quite cool, quite a simple definition therefore, just a quadrilateral with bisecting diagonals. As we said, they bisect, they're not perpendicular, equal opposite angles just like a rhombus did, because of course, as we I'm sure have realised now, squares, rectangles, and rhombi are all just special cases of parallelogram, which is why they all had bisecting diagonals, all of them. Just special cases there. Trapezium is the last one. Now, there's a bit of a disagreement as to the definition of a trapezium, but I think what's called the inclusive definition, which is at least 1 pair of parallel sides. So it could have 2 pairs, in which case it becomes a parallelogram, which means, of course, that parallelograms are just special cases of trapeziums, or it could just have 1, like the one we're looking at here. And that's basically all you need to say. There's very little going on with the diagonals at all. They don't bisect. They're not perpendicular necessarily. They could do both of those things, as I said before, but necessarily neither of those things is true. They have two pairs of co-interior angles, I guess, and that's about all you can say. And likewise, because I'm using this inclusive definition of at least one pair of parallel sides, all of the shapes that we've looked at so far are just special cases of trapezium, like all of them. And then we get to the last one, which is, and then there's a special case of a trapezium, which is called an isosceles trapezium, which has two equal sides either side. It's basically just an isosceles triangle with the top cut off. And these have one pair of parallel sides, obviously. And there is something you can say about the diagonals here. It has one line of symmetry through the middle, of course, but through the diagonals are equal, which does become relevant for one very special case thing we'll discuss when we get to our charts. But we do have equal diagonals for an isosceles trapezium, but not for a regular one. So yeah, just something that we'll mention there because it does come up in a second. Kites. Now, kites are the one that people have a hardest time defining here. Just because it's very hard to come up with a definition that includes all, like the concave and the convex ones. The easiest way to define a kite, although it's not very, what's the word I'm looking for? It's not very intuitive to tell you what a kite looks like. And I've also spelled symmetry wrong on the screen, which is amazing, love it. I'm going to continue anyway. The most basic definition you could use is a quadrilateral that has a line of symmetry through at least one diagonal. So what you could do is you could put the diagonal first, build two sides on one side of it, and then you just have to build the same shape as the other, and you get a kite, right? That's all you have to do. So just build one side, reflect it, you get a kite. Now that could be symmetrical through both diagonals if you happen to build it symmetrically this way as well, in which case you end up with either a square or a rhombus, as we said before, because they have symmetry through both diagonals, but not necessarily, of course. You must end up with perpendicular diagonals because, of course, these 2 points must be built on the same horizontal plane if they're symmetrical, so therefore these diagonals make a 90 degree. And then it's tempting to say, well, don't all kites have perpendicular diagonals? And they do, so then it's tempting to say, well, can't your definition just be a shape with perpendicular diagonals? But it can't be, and I'll explain why in a second. Of course, squares and rhombuses are just special cases of a kite, and this is also a special case of a kite where the diagonal comes, the diagonals meet outside of the shape itself, but of course that's fine. I never said the diagonals had to meet inside the shape, but they do still meet at 90, of course, because these two things exist on the same horizontal space. If you draw your diagonals first like this, with this distance, this distance, this distance, this distance, all being different lengths, you can end up with an irregular quadrilateral that has perpendicular diagonals. So you can't just define a kite to have these perpendicular diagonals, even though they always do, because there are cases where that doesn't make a kite. Squares and rhombi, as we said, are just special cases of a kite as well. Okay, so lots to get through, lots there to have got through. I'm going to put down a Venn diagram now. We started with squares, and then we said that rectangles are just squares, but without necessarily having 4 equal sides. And then rhombuses were squares without necessarily having 4 equal angles. So the Venn diagram looks a bit like this. I'm using squares to represent what you usually have as circles in Venn diagrams, just because it makes the rest of this much easier. Kites, we said, included squares and rhombi, but not rectangles, right? I did say before, right? Squares were not, rectangles do not exist in here, because they don't necessarily have that symmetry through, like they don't have, or don't necessarily, I should say, I was right the first time, have symmetry through a diagonal. So kites have to exist in the space down here, but then parallelograms and trapeziums were encompassing the things that weren't kites that we had before. So that's the bigger rectangle there, and then an even bigger one for trapeziums. So this is roughly what the Venn diagram should look like. If we have perpendicular diagonals, again, TMUA talks a lot about diagonals, which is why I'm doing so in this video. Perpendicular diagonals were all of these 3. But also be careful, because also some irregular quadrilaterals have perpendicular diagonals. So it's not necessarily, like if you've got a shape, if they're telling you you've got a shape with perpendicular diagonals, you can't just assume, that's not sufficient to just say that it's a square, rhombus or kite, right? Some irregular ones do, as we saw before. If you're talking about bisecting diagonals, that's diagonals that cut each other in half, remember? We're looking at any of those ones. Again, the parallelogram definition that we went through was anything with bisecting diagonals. So it's just going to be the parallelogram square, essentially, that does that. If you're talking about symmetry around diagonals, you've got squares and rhombi with line symmetry through both of them, and then kites with lines of symmetry through at least one, a bit like the whole trapezium parallelogram parallel sides debate. And then finally, if you're talking about equal diagonals, this is the most complicated one in some ways because rectangles and squares do that. However, you then have to build a little rectangle in here, which is your area of isosceles trapeziums, and they also do that. Even though they have nothing to do really with the other shapes at all. So that's a bit of an odd one to discuss as well. Here I'll put on the board an entire cheat sheet. If you wanted to, you could just Rain Man this entire thing. Equal sides works like this. I think I've discussed all of this in this video so far. So again, this is necessarily, right? So trapeziums could have equal sides, but they don't necessarily have any. So I've just put a note there. And then likewise, equal angles work like this. Perpendicular diagonals we've gone through. Again, you could just Rain Man this entire table and go into your TMUA exam. Just there's a star here, by the way, because isosceles trapeziums do have equal diagonals. So there's just one special case there that is worth memorizing, I would have thought. And then finally, lines of symmetry. And again, that's line symmetry, not rotational symmetry. I didn't bother talking about rotational symmetry because I thought there was enough going on in this video anyway. And also because TMUA has never asked about it. So, hey, maybe this year will be the year that they do. And that'll be really awkward. But anyway, you could, again, like I said, you could just memorize the whole thing. I apologize if there's any mistakes here. I tried my best to be careful and make sure there weren't. But there really could well be. So apologies for that. Anyway, I did promise at the start that we'd actually go through some TMUA questions. It turns out there are only 4 that they've ever asked. So let's go through them. We've got 2020 paper 2, question 7. We're talking about a parallelogram in this question. So the first thing we'll think is the trap here is to just in your mind think of that standard parallelogram shape that everyone thinks of. But if it's talking about parallelogram, it could be talking about a square, rhombus, rectangle, or that thing that you really always think of as a parallelogram. Any of those 4 things are parallelograms. So it's talking about any of those 4 things. Now, we've got one, and this is the standard parallelogram, is it not, that we all have in our head. Most people actually bend it the other way, not sure why. But anyway, PQRS, it looks like this. So if PQ equals QR, that of course means that these 2 sides are equal, which means because a parallelogram has opposite equal sides as well, or 4 sides are equal. But if you get out the cheat sheet, rhombuses and squares have all 4 sides equal. So this is not sufficient for us to conclude that this is a square because it could be a rhombus, right? So we just cross it out and say that's not sufficient. The diagonal PR intersects QS at right angles. So, okay, perpendicular diagonals then. Well, again, squares and rhombuses did that. Kites also did it, but kites aren't in the parallelogram thing. We know it's a parallelogram, so that's irrelevant. But squares and rhombuses do that. So again, for the same reason, not sufficient to conclude this is a square. And then PQR, which is this angle down here, equals QRS, which is this one here. Those are apparently equal, but just like with the rhombus square debacle that we've just been going through, we now have the square rectangle issue, which is rectangles also do that, so therefore that's not sufficient knowledge to conclude this is a square either, and we'll go with H, the answer no, no, no. Okay, 2018 then, paper 2. We've got 2 diagonals of a quadrilateral are perpendicular. So okay, we think to ourselves, which are the quadrilaterals from our sheet that had or from our Venn diagram that had perpendicular diagonals? It was these ones. Squares, rhombuses, and kites all do that. However, make sure, I did mention before, I think, that also there are some irregular quadrilaterals that also do that. I drew this one on the board earlier. So there are some irregular ones that we have to think about as well. So we're looking at these 4 groups of things, I guess. One of the diagonals of Q is a line of symmetry of Q. Is that necessarily true for this quadrilateral? Well, again, because of this irregular case, that's not necessarily true because of the irregular case that I just drew and that I've been warning you about before. The midpoints are the vertices of a square, and this is one of those times where often it's best to draw what are called edge cases or borderline cases or extreme cases. If we draw a shape with perpendicular diagonals that is like very non-symmetrical in this way, it's obviously symmetrical horizontally but not vertically, you end up getting this. And of course, if you think about where the midpoints of these lines are, you're clearly not building a square. It's actually a rectangle, and it turns out that it's always a rectangle, but again, that goes a bit beyond the brief of this video, I think. But again, neither of those things are necessarily true. And again, having all these definitions and immediately being able to draw from your head all of the different ones that meet the initial condition is very useful because it allows you to do the question quite quickly. PQRS is a quadrilateral, again, okay, sure, which is necessary but not sufficient to be a parallelogram. So, okay, well, our definition of a parallelogram earlier was bisecting diagonals, I believe. So, okay, well, we're not finding that because we want necessary but not sufficient. So that was a necessary and sufficient condition. So again, maybe that will turn up here. But again, let's just go through these one by one and say, okay, well, if PQ equals SR, let's draw them like this. So these two lengths are equal. And PS is parallel to QR. Well, guess what? I've just drawn a trapezium. So that's clearly not a sufficient condition because I've drawn something that's not a parallelogram. Is it a necessary condition for this to be equal to this? Yes, because they have parallelograms have equal opposite sides, right? And for this to be parallel to this? Yes, because they have parallel opposite sides. So we found it immediately. This is a necessary but not sufficient condition. Just to run down the other three because it's good practice. PQ equals to SR and PQ is parallel to SR. Means that it looks like this. Of course, that means that this length and this length have got to be parallel to each other and got to be equal, which means that's our overblown definition of a parallelogram of equal opposite and parallel sides, right? Two pairs of each. So that's necessary and sufficient, which is why it wasn't allowed. PQ equals QR equals SR equals PS. Well, the only two shapes that do that are rhombuses and squares, of course. And so, well, if you're a rhombus or a square, that's not necessary to be a parallelogram. You could just be a regular parallelogram or a rectangle, but it is sufficient. So it's sufficient but not necessary because, of course, these two things live in the parallelogram circle for Venn diagrams. And then PR equals QS. So finally, we're talking about the diagonals now. PR equals QS. Remember the Venn diagram I had earlier for equal diagonals. Maybe a bit of a test here. Which ones had the equal diagonals? Or that was equal diagonals, I believe, was just rectangles and squares, or was it rhombuses and squares? I'm going to have to go back for a second because I can't even remember. Which one was it for equal diagonals? I'm going to have to go all the way back. It was rectangles and squares. I was right the first time. But also remember, it was isosceles trapeziums, which could trip you up on a question in the future if it gave you that one. So yeah, this is not necessary and not sufficient, right? Because parallelograms don't need to have it, and also isosceles trapeziums do. And so therefore it's not sufficient to conclude it's a parallelogram. Good, and the last one we'll do here is 2020-2022, paper 2, about what looks to be like a bit of a kite here. We've got diagonals meeting at O, and we have all this information here, so that's fine. We can tell that this is symmetrical because x equals x, so I think that automatically makes this symmetrical if PR is a straight line. It says it's a kite, sorry, I'm being an idiot, it says it's a kite. So therefore this is 90 degrees in the middle here. Now they're asking us about SPQ, which is over here. They're asking us, well, that's a right angle, which means this is, because again, a kite is symmetrical, not that it really matters. And which is necessary and sufficient to make this a right angle here. Now I'm going to do this in two different ways. One way you could do it is because of this right angle, because kites definitely have perpendicular diagonals. Because of this right angle, this length here is root x squared plus z squared, and because of course there's a right angle there, this is root x squared plus y squared. And now, if this is a right angle, Pythagoras is a necessary and sufficient condition, right? So if this thing squared plus this thing squared equals z plus y squared, then this is definitely, if and only if, a right angle. It doesn't happen otherwise, and it will definitely happen if it is a right angle. So we can write down this thing here. We can square everything out. Most of the things cancel, and you end up with condition C. So that'd be one way of doing the question. The other way of doing it, which has nothing to do with this video at all, which is kites, of course, 90 degrees in the middle here, but also it's telling you it wants 90 here and here. That makes these two angles add up to 180, and of course 360 in the total thing means these two angles add up to 180, which means this is a cyclic quadrilateral with some center in the middle somewhere. And now a useful little fact about circles is that when you take two chords like this length times this length is equal to this length times this length. So x times x equals z times y, which is immediately condition 3. In America, they learn that as one of their circle theorems, and I've seen it called power of a point theorem. So I'll just, the only reason I would do it this way is to kind of show a point of knowing lots of other maths is also quite helpful for TMUA, not just the direct stuff that's in the spec or whatever. Other things do come in handy as well. Anyway, I hope that was helpful. I know there was a lot in there, so apologies for that, but yeah, couldn't really be helped.